Hello, I am Shukesh Roy, CEO of Spectral Energies, LLC, a small business company located in Dayton, Ohio. The topic I'll discuss today is funded by ONR and program manager is Dr. Eric Marino. The phenomenon that we want to study is the interaction of hydrometeor with the hypersonic vehicle. The objective is to provide high-fidelity experimental data of this four-dimensional phenomena, which is very complex, which then can be used for increasing the fidelity of the models that were developed to study this phenomena, which can then be used for better vehicle design or material development. And this study would require us to have a laser which can operate at megahertz rate and provides very high energy at those high rep rate so that we can see or visualize these complex phenomena under various conditions. Now, these activities are really fueled by a very unique and versatile laser platform. We call it burst mode laser that we have developed and commercialized uh, as part from our company. And this laser platform, the versatility of the parameters that we can change in this laser, allowing us to expand the application of this laser not only for four-dimensional imaging of flow phenomena, but also for other applications such as directed energy application, laser machining, and other spectroscopy and imaging techniques or spectroscopic or imaging activities. So this work is a collaborative work between Spectral Energies, Purdue University, and Southwest Research Institute. So before I discuss the specific work, I would like to give a little bit of a background of Spectral Energies capabilities. So when it comes to laser-based sensing and measurement, we have done enormous volume of work in various hypersonic wind tunnel and RDE diagnostics. All of those facilities and the experimental setup requires very high-speed measurements of flow parameters such as velocity, temperature, chemical species concentration, and in a lot of those activities, even a point, line, and planar measurements are not enough. So that means we need to do four-dimensional. So we have led the development of four-dimensional measurements of reacting and non-reacting flow parameters through utilizing the versatile burst mode laser. We have developed as a commercial product for imaging of chemical species, thermometry, and velocity field. And these are part of our core activities. We have also activities in terms of ablation diagnostics and directed energy application. And of course, we are a company, when it comes to laser, we take the lead on a lot of the solid-state laser engineering and packaging, and a lot of those lasers are not commercially available. When we find an application and we realize we'll need a laser that doesn't exist commercially, or it might exist, but it might take an entire room. So we think about how to develop a commercial product which can be easily transported in various labs around the country. So our developed laser or the burst mode laser, we have taken to various facilities in and around the country and internationally, and able to provide groundbreaking measurements when it comes to hypersonic and rotating detonation engine experimental setup. So as a company, our company was set up, or we started the company in 2006. So we have been working for 16 years. So we have a lot of expertise in system integration, technology transition, and commercialization. And of course, we, as I said, that the key technology that is fueling the growth of our sensing and measurement capability of this company is fueled by this versatile burst mode laser. We have also recently developed, using the similar platform, developed laser which can operate at 10 hertz system up to 20 joule per pulse in a very compact package. And we have a proven track record for making measurement in many hypersonic facilities in and around the country. So in terms of key resources that we have the highest energy commercial burst mode laser system. We have megahertz rate cameras, hyperspectral imaging, and we have established a test bed for really exploring the application of this laser for directed energy application. And we have a team of core 35 employees. Out of that, 25 people have PhDs, and then we work with many universities, and there are approximately 30 to 35 graduate students are funded by various programs and in collaboration in many collaborative projects with us. And our team, we have activities on other areas, but when it comes to hypersonic, we focus on laser engineering and effects, hypersonic flows, nonlinear spectroscopy, combustion chemistry, and to a limited extent, some modeling. And of course, we have other activities in AI, machine learning, and developing, looking into other aspects of hypersonic vehicle, hypersonic system. So what is the challenge for Navy? Is that, or what is the interest of ONR for funding this project? The challenge is to understand the effect of adverse weather on the hypersonic flight. And this effect is not well understood because of lack of experimental data or inability of the current model to really model this complex phenomena in detail. So hydrometers such as rain, hail, and ice will disrupt the flow field. And not only it will disrupt the flow field, it will also modify the surface, vehicle surface, that in turn will modify the boundary layers and the performance of the vehicle. And that will pose serious damage or serious risk to vehicle moving at hypersonic speeds. And as I said, the modeling and understanding of these weather encounters are not very challenging and not that well understood because existing computational models cannot capture these complex weather effects yet. The solution is to provide high fidelity 4-dimensional measurement. When I say 4-dimensional, 3-dimensional in space, because these flows are going to be very complex and 3-dimensional. So our measurement system has to meet those challenges. So that means we need to provide 4-dimensional measurements in some of the hypersonic ground test facilities that we have in the country, so that we can shed light into the physics or the effects of these weather events at hypersonic speed. In particular, from this program, we are focused on really understanding the impact of rain or water particle on modifying the boundary layers, flow fields, and the vehicle surface. So the requirement is that our measurement, of course, has to be non-intrusive because you cannot have a physical probe. So those non-intrusive measurement has to be able to capture this highly complex flow field with a time-resolved manner. So when we talk about hypersonic flows where Mach number is normally greater than 5 and higher, we need to have a measurement system which can resolve this time-evolving phenomena at their speed. So that means we need measurement technologies which can capture data at megahertz or even 5 megahertz, 10 megahertz rate. So our versatile laser platform is allowing us to visualize this flow phenomena and capture flow physics for various ground test facilities where experiments are conducted at Mach number 5 and higher. The primary droplet diameters that we are dealing with normally varies between from 300 micron to 3 millimeter. And for the primary droplet, for secondary droplet, we are devising imaging system which can resolve 0.03 millimeter to 0.2 millimeter or 200 micron, and ice crystals between 1 to 50 micron, and that's going to be part of our future activities. So now a system that is developed, maturized for these activities have a really big potential for transitioning this technology or transitioning this versatile, transportable, and laser platform for other application, specifically for industrial high-speed, high-precision laser machining, and from a defense point of view, from really provide a platform, pulse laser platform for investigating directed energy effects. As I have discussed in the previous slides, the challenge is to provide high-fidelity measurements of interactions between hypersonic projectiles and hydrometers, which are required to inform hypersonic flight models and determine flight risk, such as aerodynamic instabilities and cone tip damage. And if we can provide insights into this complex flow physics through an unique set of four-dimensional measurement, it will significantly benefit not only Navy, but Air Force hypersonic flight development, NASA flight studies for industrial super and hypersonic aircraft, including commercial aircraft and defense system. As all of us know, there are a few companies which are really investing in a lot of supersonic and hypersonic commercial flights. Typically, these measurements are limited to path-integrated 2D imaging as shown in this figure. In the figure, what we are showing, a projectile is hitting a water droplet or series of water droplet, as you can see because of this, and you can see the shock wave that was generated from this interaction, and when this droplet comes under the effect or effect of these shock waves, and they interact with each other, and they strip away, and we call it shear stripping. So that way the droplet size get aerosolized, and then the spray, it creates a spray, and it creates a breakup of the spray through the projectile shock front, and then it creates a cloud, and those clouds and all those things are interacting with the vehicle surface. As you can visualize from this set of four pictures, these are done through two-dimensional shadowgraphy, slit imaging, and these shadowgraphy and slit imaging are line of sight in nature, so you don't know what's going on in the three-dimensional way. It's a average along this line of sight, so it doesn't provide you, it can provide you something in terms of qualitatively what's going on maybe, but you don't know what's going on in the depth direction. What we want to understand, how these droplets get transformed or being aerosolized with this interaction, how these shock waves gets modified, and then how they interact with the surface. So this typical two-dimensional measurement might provide some information, but it's not really enough to understand this complex flow physics in a very systematic way, or in a way where it provides basic understanding of this entire flow interaction. So if we do high resolution tomographic images, then it will allow us to look into the flow field from a, for example, let's say 360-degree view. And this is what we plan to provide under our program. And as you can see, these are very highly complex time evolving phenomena. So that means providing just 3D measurements at, let's say, 10 hertz or 10 measurements per second is not enough. These flows are evolving very fast. So that means we have to do this or capture this three-dimensional flow phenomena in microsecond or even faster than microsecond time scale. And this is what our technology will provide. So in terms of solution or the technology that we have developed for this program, as you can see, the picture on the right-hand side is showing a shadowgraphy of the projectile interacting with a stream of droplet. It's creating a spray which is kind of opaque. So we picked out an area where, as you can see, it's shown by the purple box. We have picked out an area where there are true droplets which are under the influence of the shock, various shock wave that was generated because of this high-speed projectile moving at up to Mach 5. For this particular experimental setup, we want to see how those true droplets are evolving in time and their interaction. And the approach that we have undertaken is that we have doped these droplets with dye so that when we shine laser light through that, they will fluoresce. Those dye will fluoresce. Then we can see a three-dimensional clear picture, highly resolved clear picture of this evolution of these droplets as they interact with these high-speed flow field. So this novel imaging system, we have developed a full tomographic system where we use multi-view illumination, because for us to see the entire three-dimensional droplet interaction very clearly from all directions, we need to illuminate the droplets from all directions. So we have used 4 views from one direction, then we use another 4 views from another direction. So we have 8 views for this reconstruction. And those entire technology was developed under this program. This is uniform volume illumination, utilizing the same set of optics we used for signal collection. So not only measurements are being performed at megahertz rate, that means with microsecond resolution, we have also devised a strategy so that we can look into the evolution of these droplets in a spatially resolved manner. And for this, if you look at the picture in the bottom that shows those 2 droplets that we highlighted with the purple box, and And as you can see, when the time went from 80 microsecond to 100 microsecond, those two droplets were separated initially, and we looked at their evolution. By the time they're at 100 microns, those droplets are being aerosolized because of their interaction with the shock wave and the flow field. And as we move along the time, they will merge and become a one droplet, and then it will create a small particle. So the primary particle droplet size we have investigated for this particular set of experiment is 300 micron to 3 millimeter range. So if I have to highlight the key innovations, those are the high-speed, high-energy laser for complete volume elimination from multi-view, and then resolving the temporal evolution of this field. And so we have done fully tomographic laser-induced fluorescence where these droplets were doped with a dye so that we can capture highly resolved view of the evolution of the droplets under the influence of various shock interaction and the flow field interactions. So the current milestone that we have to demonstrate three-dimensional Mie scattering with droplet, three-dimensional laser-induced fluorescence with droplet, identify test location and design architecture, and perform initial hypersonic hydrometer measurements. What we have done, we have completed measurement with a spatial resolution up to 600 micron. We have developed the full imaging system setup, laser parameters that are ideal for facilities like Southwest, but we have to develop imaging system and setup which are more robust for ground test facilities that Navy has, Army has, and Air Force has. And the initial measurements that we have performed where Mach number was limited to around 5.5, and we have demonstrated successful imaging at gas gun test site. As I said, the future milestones will involve this harden the software resolution and integration, because right now, even after we do all these experiments, it takes enormous amount of time for us to analyze the data. So we want to increase the robustness of the software, and then for higher level ground test facilities, we would like to harden those imaging system with imaging fiber, and at some point in the future, we would like to integrate ice particles in the experimental setup. And in terms of risk reduction, since these are all very challenging work, we feel like the background and the experience we have, we are well suited to carry out these activities with a reasonable risk. In terms of funding, we have the phase 2. Phase 2 funding is done, and we still have a few more months in the complete phase 2, and then we'll go to phase 2 option and hopefully prepare for phase 3 transition. Our laser is at TRL 6 level, but we think we can make it to TRL 7 level so that it's suitable for challenging ground test facilities where you don't have very well-controlled environment. And our imaging system is at TRL 3 to 4 or 5 maybe, and we want to take it to TRL 7 through replacement with imaging fibers and various other hardware integrated three-dimensionally machined hardware and stuff, so that instead of individual component, the entire imaging system is one component machine from 3D machining. So I would like to say a few words regarding the key features, advantages, and the benefits. As I have discussed throughout this presentation, is that the baseline measurement challenge is measuring three-dimensional measurements of hydrometer effect on hypersonic aerodynamics. Mach number generally greater than 5, particle sizes between 300 micron to 3 millimeter, and the baseline capabilities are normally what is the current state of the art before our measurement was limited to Mach 2, maybe Mach 3. Three-dimensional is not available, and it requires very complex and sensitive setup. Our technology that we have developed, not only the laser, but the entire imaging platform is we have demonstrated up to megahertz rate tomographic imaging using laser-induced fluorescence. We have made the measurements at Mach number of 5, and we went up to droplet size of 1 millimeter with sub-millimeter resolution. So if you look at improvement, we have done 2.5 times improvement with pathway to greater than 5 times improvement in terms of image resolution, and then in terms of increasing the dimensionality of the measurement system. And we have done 3-dimensional with sub-millimeter resolution while or without sacrificing our temporal resolution. So our temporal resolution is 1 microsecond, so that means at megahertz rate. And the laser platform is very compact, transportable, and ready for prime time for all sorts of commercial use. And we strongly feel that these new capabilities that is developed here will fundamentally improve our understanding of a hypersonic flight through clouds and provide invaluable data to support our numerical model. So in terms of market analysis for this product and this kind of work, of course, we looked at the hypersonic resources that have been utilized for hypersonic related research activities. We think the current market is around 2.6 billion. Of course, measurement is going to be a very fraction of this total dollar value, but the total revenue is expected to grow additionally, even additional 5 billion annually through 2025. So if the total budget improves or increases at this kind of scale, we feel there is a significant room for budget or significant room for budget increase for measurements and high fidelity data from various ground test facilities. And of course, we also see market with the commercial hypersonic defense contractors like Lockheed Martin, Raytheon, and Boeing, commercial hypersonic flight, or even supersonic flight. Some of the things we are studying for hypersonic are still going to be very important or applicable for even supersonic flight going at Mach 2, Mach 3, Mach 4. So there are a lot of commercial companies which are getting into this business. So we feel based providing all those measurements, we can generate several million per year in sales of either measurement system or the services for those measurements that I have laid out in this presentation. So within the government, we would like to, these technologies that we are developing will help support further activities with Navy, Air Force, and NASA in various ground test facilities in and around the country. So we believe that a lot of these facilities will either buy products from us, full system, or they will buy our services. So we expect to deliver 2 to 3 products per year within the next couple of years. So in terms of transitioning this technology and partnership with other DoD labs and commercial partner, immediate transition of technology, we feel like this laser platform where it's very versatile in terms of pulse width can be varied from millisecond to all the way to picosecond in one laser platform. And of course, we can add additional feature from going from a few picosecond to femtosecond. So we feel like this can be a workhorse, and for directed energy application, for pulse ablation, for secondary RF or microwave generation, and for infrared countermeasures. And the other application is to really increase the speed of laser manufacturing in terms of high speed, precision, three-dimensional printing, additive manufacturing, and novel material processing. So key partners that we consider that would be critical for our technology to become the go-to product for some of these areas I have discussed are through DoD labs and commercial partners. So we are actively discussing with various high-energy laser labs within ONR, NRL, AIRP, and other branches of the DoD. And our commercial partners, we are in the process of starting the discussion with various commercial laser company where this can be integrated with for various laser-based machining platform or welding or laser pinning or other display processing infrastructure. In terms of funding and to maturize this product even further, we expect the funding for $2 to $3 million per year for further laser process development, for remote effect testing, maybe increasing the range in the kilometers, and for various aircraft material testing and for other directed energy applications. So these are the areas we see immediate transition and partnership opportunities. So for future collaboration, you can reach out to me or my partner, Dr. Sivaram Goginini, who is the president of Spectral Energies. Contact information is there. You can reach out to our company phone number, email address, and to really try to get a broad overview of our projects that we are dealing with. Please visit our website, www.spectralenergies.com. In summary, what we can provide is unmatched hypersonic imaging capabilities, and those same technologies are ready for deployment in rotating detonation engine research activities, test cells, and any other aspects of high-speed flow phenomena. And we can also provide you the laser source supports, where if you don't have the funding to acquire this technology, you can work with us so that we bring our laser and imaging platform to your facility, and we are ready to have the opportunity to work with either defense or commercial partners to further develop this technology for your specific applications. Thank you very much.